blocks long.
How could you read Ender's Game and not look to see if there were more?
Because it was an okay book.
It's better than okay.
It's okay.
I read it all the time.
No, the movie's Ender Game was a joke.
You like the book. Yeah, it's a book that we read in common.
And you thought it was like worth, like you didn't waste your time reading it, is your feeling.
No.
But
I didn't.
But it wasn't a life-altering thing.
Right. It wasn't like you said the life-changing book, Ready Player One.
Yeah, but I mean, I would say Ender's Game is probably in my top 5 best books.
All right.
Ready Player One's number one, easily.
Okay.
Okay, so let me go back and review something. It was brought to my attention after class last time that I was referencing a slide several times that I didn't actually have. I've been teaching for a few minutes. So, yeah, so I wrote this for the student when they came to my office. So you've heard me referencing this idea. Let me just kind of give you some context here. We talked about how C++ had structs as well as classes, right? But we never really talked about what a struct is. I've referenced, oh yeah, you got a first name, last name thing, and I think I've had you read up in the book so far. Have you read in the book up through dictionaries?
No.
Okay, we've been just doing the Mendic stuff. Okay,
Yes.
So yeah, I got some crossover with another class. Okay, so in any case, if we look at what a struct is, so this is a struct up here. Forget about what its name is. You know, struct and class, they look pretty similar anyways. But a struct is going to hold on to something like these are strings. So a struct might remember that we have a first name that's going to be a string. We're going to have a last name that's going to be a string. We're going to have an age that's going to be an integer. So we can hold on to pieces of information that are just name value pairs. First name, Mike. Last name, Littman. Age, 21, that kind of stuff. So it's just holding pieces of information in name value pairs, as opposed to, let me just throw it all in here. Let's, can I steal this one? No, let's just throw it on another slide. As opposed to a array, which we've referenced several times, but just to kind of clean all this up. So if I create an integer array capable of holding 10 things, that's going to be too many. We're going to create 4 things so I can draw it quicker. That's going to create a structure that looks kind of like this. All right, so to kind of pull these things together, we've talked about like one of the problems with C++ was that it empowered the programmer to make kind of bad choices. We could pass somebody the house versus pass them the address of the house. So we have this thing in, we actually already wrote it in here. We have this thing in programming called a pointer, which is just a variable capable of holding a memory address. It becomes very scary for, did I show you Hello World last time in C? I read some C stuff last time, so we saw scary looking memory addresses, that kind of stuff. Yeah. Okay, they look intimidating, but I probably referenced that our addresses in real life are very complex, where addresses in computers are just one long street, and if your house 14 zillion down the street, you just got a long walk. Okay, but it's just right down the street. Just keep going through about 9,000 traffic lights, and it'll just be down there on the left, something like that. All right, so pointers feel intimidating to us because they look scary with all the hexadecimal stuff. All right, now I've created a very simple pointer here. So in our modern programming languages, we have this new keyword called new. And this guy goes and gets us some memory from the operating system. Don't worry about that in the big scheme of things. Just know that that guy is going to give us some memory. He's going to give us a plot of land somewhere along that street for us to put our thing, put our house or whatever, okay? So let's just say in this example, he went ahead and assigned me memory address 100, okay? Just to keep it simple, because that's not that scary of a number, right? All right, so he gave me memory address 100. Now I asked him for a big enough plot of land to hold that many, 4 of these guys, 4 integers. Okay, now an integer in most modern languages is 32 bits or 4 bytes. A byte is 8 bits, so 4 times 8 is 32. Okay, so 4 bytes, 32 bits, same number, right? Okay, I don't have 32 fingers on this hand, so. All right, so we got 4 bytes. So that means I'm going to need, for 4 of those things, I'm going to need 16 total bytes. All right. Now, so what it's going to do is it's going to create this structure in memory that looks like this. It's actually just creating this guy, just the middle part. This is where my values would be held. And I'll go ahead and pretend like we went ahead and filled this. So I'll put a 4 there, and I'll put a 21 there, and I'll put a -2 and a 1. We'll pretend like we've gone ahead and filled this array up with some values. This guy right here doesn't actually fill it. It's like going to Target, getting a little container that has 4 cubby holes in it, but I haven't put anything in the cubbies yet. Okay. Make sense? But now I've put some stuff in there just so we can kind of see where, how this whole thing maybe plans out. Okay, so what I have here is a variable named AR. And if I were to print out the value of AR, it would print out 100, the memory address. So AR holds a memory address, which means that AR is a pointer. He points to a place up in memory where my array can be found. Now, we've said that arrays are effectively collections of like values. All right, so I have 4 in this case. I have 4 integers. So they're all the same kind of value. So this is a 4, a 21, -2, a 1. Now, how these differ from structs is notice that with a struct, this one structure, I can have, in this case, I have 3 buckets, okay? 2 of my buckets are holding strings, the other one's holding an integer. So I don't have to hold the same kinds of values inside of a struct. That's step 1. I could choose to hold 300 integers if I wanted to, but I don't have to. Step 2, or perk 2 with a struct, is I get to label each of my values. So in a struct, I can say that this value is the first name, this value is the last name, this value is the age. So I get kind of a collection of variables that I can house inside of this single thing called a struct. All right. Where with arrays, if I wanted to say that this was the, we'll have to give meaning to these numbers. This is the guy's basketball jersey number. This is the number of points he scored last game. This is the number of points he cost the team or something like that from turnovers. And I don't know, this is how many minutes he sat on the bench. Okay. So something like that. We would have to remember that bucket 0 holds his jersey number. Bucket 1 holds the number of points he scored last game, that kind of stuff. So that's kind of assuming quite a bit. We could do it. It's not impossible, right? But that, we'd want to definitely document that. We'd want to throw a comment before that saying, here's what those buckets mean. Probably not the best tool for that job, but we could do it, right? Yeah. That would work. That goes up against how human beings solve problems as well. We work with the tools that we have, and if you have 4 little cubbies that are that are not labeled or anything like that, and you need to throw some stuff in there, I'm kind of thinking I fish, so I'm thinking about it from like a tackle box perspective. Like your tackle box when you first fill it up is always nice and organized. And that lasts 1 fishing trip. And the next thing you know, the stuff is in there somewhere. And it's always very interesting when you have to dig through and there's hooks. That was the thing. So in any case, that's a weakness of arrays, is that you don't get to label the individual values. Okay, but so you might say, oh, why wouldn't you just always use structs then? if structs are better than arrays. On the surface, they do. They seem better, right? Okay, well, first of all, creating an array was just that one line. Creating a struct, this is the creation of that struct right here. And then I went ahead and I created one of those. I created a person named P. I set P's first name to Mike, last name to Littman, age to 21. I can then create another one of those structs and set first name to Sally, last name to Smith, whatever. So I can create multiples of these. But the setup maybe is a little bit longer, especially if you're going to store lots of pieces of information. Okay, well, you might say, oh, well, it may be worth it because the convenience of using it after that is good. Okay, well, arrays are also really, really, really fast because of how they're organized in memory. So arrays, and I'm not going to go too deep into this, are stored in what's called contiguous memory, which is a fancy way of saying memory in a row. Oop. There we go. Fancy way of saying memory in a row. And what I mean by this is, let's say that I wanted to get the value. So notice that down here I've indexed these things 0, 1. Oh, that was a very strange way of counting, wasn't it? Okay. 0, 1, 2, and 3. That would have been a very important skip. You're going to see why in a second. Okay, so this is kind of how human beings want to index it. They want to say, oh, I want the arrays are, as well as strings are all indexed from bucket 0. So if you have a 4-bucket array, the legal buckets are 0 to 3. All right. So a human would say, oh, I want whatever value lives at bucket 0, or whatever value lives at bucket 1, or whatever value lives at bucket 3. As opposed to a human saying, yeah, go ahead and give me the value at memory address 112. In an older language like C and C++, you can say, give me the value at memory address 112. No problem. Okay, you can do that because, and I'll actually show this to you today because we're a little compressed on time because I was late, but just to kind of bring all this together, that's not comfortable for a human. But we could do it. And let me show you that. Let's go back out here to the terminal. What did we name our file in here? Was it test.c? Is that us?
Yes.
Close enough. This is a good enough thing to erase. All right, so what I'm going to do is I'm going to use a little bit older language. I'm going to go ahead and create that, that same integer array. All right, so I'm going to create an integer pointer called AR, and this guy is going to equal, I need to include another thing here. Don't worry about that. I'm not going to be quizzing you over anything with C. I'm showing you under the hood stuff so you know where modern programming stuff comes from, okay? You'll do C stuff when you take 450 with me.
Okay.
All right, so I'm going to create a variable of type integer pointer, which we've learned in here. This is just a variable capable of holding a memory address. And it happens to be a memory address that points to an integer. Make sense? That's what it holds. That's the kind of value it holds. I could have also created an int called A, and that guy's a variable capable of holding a number. This guy's capable of holding a memory address. All right, so now I'm going to allocate. This actually isn't required in modern C, but I'm going to do it anyways. So I'm going to allocate some memory. How much memory? I want 4 times however big an integer is. And I want you to give that to me in an integer pointer. By default, it gives it to you in something called a void pointer, which you'll see what I mean by this here in a few minutes. All right, so this line right here, in fact, I'll go ahead and steal that line. And this line, good enough, do the same thing. All right, they do the same thing. Now, if you're a more modern C++ programmer, you could actually pull this off. You could say int AR2 4. That's what the weaklings would do. And that does the same thing. Actually, sort of does the same thing. That does it in what's called literal space versus active memory space. Unimportant to us, but you'll never do that when you have a class with me, because when we're using C, we're in systems programming and we want to really manipulate memory, because that's something we're going to do a lot.
Okay.
So this is what the cool kids would do, right? This is like the skateboarders who do all the crazy tricks without pads. Yeah, that's us. All right. So these two things ultimately do the same thing. They build something that looks like this. All right. So now what I'm going to show you down here is if we want to get to bucket 0. I've shown you that bucket 0 is at memory address 100. All right. Now just to give you a quick little peek here, I'll go ahead and do a printf %p\n. We'll print out AR. This is going to give me the memory address of AR. So the equivalent of that 100. Really, really, really low chance this is going to be 100. Actually, 0% chance, because this is the Unix operating system, and the first, I want to say, 700 kilobytes of memory is reserved for the operating system. So we're definitely not getting a memory address 100 from this. What was the... Oh. Didn't I do that last time? Flip. Print. Yep. Nailed it. All right. So that's the equivalent of our memory address 100. Okay. We call that guy, so in this case, that 100, we would call that the base address of our array. That's what that 100 is. We just call it the base address, where the array starts in memory. Now remember, I've mentioned that arrays are contiguous, which means they're stored all next to each other in memory. So if we know where it starts, and we know how long it is, and we know how big each value is in the middle, we can take that size step to go from value to value to value. Does that make sense? Now, as humans, we'd like to say, oh, well, go ahead and give me AR at bucket 0. Nice and simple, right? And that's going to give me a 4 in this case. What this is actually doing is it's saying, go to base address AR, add to that 0 times whatever the size of the type you're storing, which in this case is an integer, which is the same thing as saying, go to memory address 100 in this case, add to it 0 times 4, which is the size of int, which is 100. Bucket 0 is memory address 100. If I want to go to bucket 2, so if I take this exact same thing, we'll just modify this one, and I say I want to go to bucket 2, I'll say start at the base address AR, then go to 2 times size of int, which is 100 plus 8, which is 108, which is the memory address of bucket 2. All right, so we are taking integer size steps through memory. Because when we ask the operating system for some memory, we're saying, hey, I need enough memory to hold 4 integers. Okay, and we know that 4 integers, an integer is 4 bytes, right? 32 bits, so it's 4 bytes. So to hold 4 of those, I'm going to need 16 bytes. I need a plot of land 16 bytes big. All right, now when I take my steps here, I'm saying I need to take a step size of size int. So if I'm starting at the base address of memory, let's say we're going to do these little squares here. Can I do 4 steps? Yeah, probably. Okay, we're going to have these little squares here. So I'm at the base address. If I want to go to bucket 2, I need to take one 4-byte step followed by another 4-byte step. Now I'm in memory at bucket 2. But if I was storing chars, which in a language like C are actually 1 byte big, because C uses what's called ASCII instead of our modern languages use Unicode, which so ASCII is 256 characters, Unicode is 65,535 or 536 characters. finally we decided that there's other languages in the world other than English. All right, so, so if we were doing the same array, but for 4 chars, 4 bytes, I'm only going to need 4 buckets. So when I want to go to bucket 2, I'm going to take a char size step and another char size step. Now I'm at bucket 2. Because 4 chars will only require 4 bytes, a lot less memory. That makes sense? So this is the size of my step. So when I say I want to go to I'm going to start at the beginning of the array. I'm going to take this many steps of this size. That's going to walk me through the array. That make sense?
Yeah.
Now, in a language like Java, we can't do this. In Java, if we want to access bucket 0 or bucket 2, we do it this way, just by saying AR at bucket 0 or AR at bucket 2, which as a human we can appreciate. Like, oh, that's easy. It's easier for us to. I don't want to work. I don't want to deal with memory, even though under the hood we're dealing with memory. Okay, but to understand this, if we go back to a language like C or C++, and this hopefully closes some of the gap here. In a language like C or C++, we have a specific syntax for working with memory. So if I say that I want to get to bucket 2 of this guy, I'm going to go ahead and fill this up with some stuff. So I'm going to say AR at bucket 0. Here we'll actually match our thing. I'll show you both ways. So AR at bucket 0 is equal to that. AR at bucket 1 is equal to, what do I have there? 21. AR at bucket 2 is equal to, is that the negative 2?
Yeah.
And AR at bucket 3 is equal to the 1.
Yes.
All right, then if I come in here and I say I want to print out the integer that lives at AR at bucket 2, oh, sorry. I need to make a small little change there. Because of the way I built it, it might not actually let me do this. But I can at least show how you do it. Yeah, it's not going to let me do it. That's okay. I'll show you the extended way. So I want to say something like that. I want to say just AR at bucket 2. But it's not going to let me do that. Instead, I'm going to have to spell out. I'll spell out to Siri. You're welcome. See, on this laptop, we have this little magic pad thing up here, and on the far right by the delete key, they have the little Siri button. You hit it all the time. It's like stupid. Terrible design. Okay, so I want to print out I want to get the value that lives at memory address AR plus 2 times size of int. So I want to take 2 integer size steps through memory, add that onto wherever the array started at AR, and then I want to say give me the value at that position. Does it not like the way I filled this? It might not like the way I filled the array. Star AR. Oy. Here, just to keep it simple here, I'm only going to go to bucket 2 or bucket 0. Star AR plus, well, actually I could do it for bucket 2, plus 2 times size of int is equal to, was that the negative 2?
Yes, now.
What are you upset about? I'll give you just a warning. Maybe that was the problem. Oh, the whole thing, I've been just stupid. The other thing probably would have worked. It's a % symbol, not a $sign. There's your negative 2. All right. And similarly, here's just the appease our souls. I could have said AR at bucket 2, I believe, here. Oh, interesting. Is it because I filled it this way? Yeah, interesting. Because one's a literal, I mentioned a little bit ago, one's a literal in C and C++, the other one uses user space. Just a thing. But in any case, for us, we like the longer-winded version of this. All right, because it makes us feel cool, right?
Yeah.
So we'll go ahead and say, give me the value that lives at AR plus 2 times size of int. Actually, this will be interesting because I think this will still be literal space. Yeah, still in literal space, so that I would have had to fill it in a compatible way to that. So I would have had to do set the value at AR plus 2 times size of int equal to -2. And there's my -2. All right, so this is kind of what I'm showing you how arrays work under the hood. I'm creating my array, which is giving me the base address of AR, followed by enough land to hold 4 of these guys. Then I'm going to go ahead and I'm just directly filling bucket 2 of that array with a -2. So I'm saying go to the base address, add to that 2 times the size of an integer, and that'll take me to what we think of as it'll be the third integer in there because it's bucket 0, bucket 1, bucket 2. And I want to store at that position a -2. Then when I go and print the number that lives there, I will print out the value, that's what the star says, value at this base address plus 2 times size of int. All right, and that'll give me the value that lives there. If instead I want to know the memory address that lives there, I would say, show me the pointer that lives at that address. So that's where that -2 lives in memory. That make sense? That's a pretty good hike down the street. It's up the street. All right, so that's how arrays actually work under the hood. In a modern language, they don't, well, in a modern language like Java, they don't allow us to manipulate the memory directly. Therefore, we can't choose to use it in the way we just used it, walking through memory, taking integer-sized steps, and that kind of stuff. Which on the surface, you might say, well, that's good. As a human being, what we just saw there, fine, it seemed cool and all, but you really should wear pads while you're doing skateboarding, right? We can say that. So, you know, we probably want things to be more convenient for us. We don't want to have, I mean, there's a lot of room for error when we're writing something like this, right? There's a lot of extra pieces that we can, now, but having said that, the idea is that when you're writing, maybe if you're using C++, you're using a modern compiler for C++ that lets you use some of the modern syntax without walking through memory, you can, maybe 98% of the time, you would use the convenient modern syntax because you don't need to access the underlying memory. If it's existing in literal space, that's fine. Who cares? Let C++ handle it for me. But every now and then you might run into a problem where having control of the actual memory might benefit you. And in a language like C and C++, you are allowed to participate with real memory. You can choose to go in and manipulate real memory. Where in a language like Java, they've taken that ability away from you. Okay. Does that make sense? Okay, so we don't get those tools, so we can't decide to go in and work directly with real memory, which maybe hardly ever will hurt you. In fact, maybe it will never in your entire career hurt you. But if you're doing very specific types of programming, it might be beneficial to directly be able to access memory. All right. So if we go, I'm still here. Go ahead.
How does Python, like, how is that compared to this? Like,
More like Java.
Okay.
So Python hides it from you. You can't directly access the memory address. And that's a pretty that's a truth across. I can't think of one that this breaks. I'll just say a truth across all interpreted languages.
Okay.
So Python is an interpreted language, and part of the nature of an interpreted language is they are easier to write the language because you're writing an interpreter rather than a compiler. So you're solving an easier problem, and because of that, you've kind of given up direct access over memory anyways, because you're laying on top of the operating system rather than interjecting to the CPU. You're communicating with your computer at a much higher level in a language like Python because you're going through an interpreter. All right, so in any case here, when we look at a struct just holds name-value pairs. Okay, so we have a name, and then it would have a value associated with it. We have a name, and it would have a value associated with it, so on and so forth. Now, we might decide that it would be handy to be able to have functions that operate on that. Like, for instance, let's say I want to know how old I'll be in 5 years. If I'm working with structs, and I want to have a function that knows how to do something related to myself, I would have to have that function live outside of the struct. And then I would have to pass the struct into that function. I would return the age of whatever was passed in plus 5, and that would be their age in 5 years, right? Kind of a simple little math. How old will you be in 5 years? It's your age today plus 5. That's how old you'll be in 5 years, okay? Yeah. But the thing is that this guy right here lives outside of my struct. This is my struct up here. Where classes allow us to bring functions like that inside of the class. So it's like a struct, but it has the ability to store functions in there as well. So now we have a new kind of value. Here's the name of that variable, and its value is a function that returns an integer. The name is last name, its value is a char pointer. Name is age, its value is an int. Now we have something whose name is how old in 5 years, and its value is a function that returns an integer and takes no parameters. That's what its value is. That's called in language theory, it's called a lambda expression. So its value is something called a lambda expression. Also unimportant to us in this class. All right, so we've added a new name value pair type in classes, which allow us to embed functions within the class, which then allows us to say something like, okay, here's my person. Go ahead and fill out person's name, all that stuff. So, you know, these 4 lines here are pretty similar to these 4 lines here. This actually isn't how you would probably do it with classes, but you can do it with classes this way. I just wanted to make them look identical. All right, it's legal. That's probably not the way you have a more convenient way of getting data in there than that. But then you can ask the class to say, how old will I be in 5 years? And it would then spit out the age of that internal person plus 5. Where out here, if I want to know how old I'll be in 5 years, I'll have to call how old will I be in 5 years, passing it my person. So I would do something like this. Oop. How old in 5 years, and I'd pass that guy P. So over here, when I called it, notice that right here, how old in 5 years, I didn't have to give it any information. It already knew about the values of P. Where over here, I had to say, how old will I be in 5 years? I'm calling that function, but he needs some data to operate on because he didn't live inside of the struct, so he didn't know about that data. Go ahead.
You have to write, like, I mentioned how old in 5 years. Did you write that as its own function, like, make it a statement for it?
Well, over here, I wrote it as its own function, which is unimportant to us right now. Yeah, but just in the big scheme of things, structs did not allow us to put animals that looked like this inside of them. Classes did. All right, for us, that's the distinguishing factor. All right, so, but then I was talking last time, I know we're out of time, let me just say this as a zip up. So that brings it together what we were talking about last time, where we were talking about pass by value versus pass by address. And Java specifically says that, oh, well, you need something like a struct, just create a class that doesn't have functions in it. Okay? But classes by default are passed by address. Structs by default are passed by value. So even if you create a class and choose not to put a function inside of it, it still gets passed by default to other functions slightly differently to how structs are. And I kind of show the example of that down here, where if I create a function, try to change a value, and I pass it a struct, and I print out the value first, and I try to change it in here, that value will not have a permanent change because that struct here was passed by value. A copy of that struct was sent into this function.
Okay.
Where over here, if I do what looks like the exact same thing, a pointer to P was passed into this function. So when I changed P's age here, that's a permanent change. It happens outside of that function from that point forward.
Okay.
So they act a little different under those circumstances. All right, questions, comments, concerns, bribes. Do we have 2 more modules in Mendix, or are we done?
2 more.
All right, so last 2 modules in Mendix for
Wednesday.
Wednesday, and I'll put up the Bible homework as well. And once again, sorry I was a few minutes late today.
It's one module in the test.
Oh, that's fine.